Hi, my name is Daniel,
And I'm Luke.
and we are solving problem number 13 for this video project. So, before starting the problem, we made sure that we set up our coordinate system. So, we set up the positive direction of y to be going up, and then positive direction of x to be going to the right. And we have our givens right here with the mass of the cart equaling 6 kilograms, with the mass of the hanging mass equaling 8 kilograms. um, Mu static equaling 0.45 and mu kinetic equaling zero point 0.2. So before starting with solving the problem, we made sure that we made sure that we drew our force diagrams for this problem. So here are the force diagrams for the hanging mass, which is right here. And for the hanging mass, the forces acting on it are the tension pulling it up and gravity pulling it down. In the meantime, we also solved for gravity, which equals we solved for the gravity of the object, which is equaling to 78.4 newtons. And after that, we decided to draw the force diagram of the cart, which is right here, with gravity pulling it down, and then the normal force pulling it up, and tension pulling it to the right, and kinetic friction pulling it back to the left. So, meantime, we also solve for the gravity of the cart, which is 58.8 newtons. And by solving for the gravity, we also get the normal force of the cart, which is also 58.8 newtons. We solved for the static friction right there, and it had to in order for the object to not move, the static friction had to be equal to or less than 26.46 newtons. And we also solved for the kinetic friction, which equaled 11.76 by multiplying the mu k times the normal force, which equals 11.76. Now Luke will go on to explain how we set up the system of equations.
So this problem is asking us to solve for the tension in the string. And by Newton's third law, we know that the tension in the string, tension 1, which is between the coat in the string, is equal to the tension between the hanging mass in the string. So we can set up this equality here. Next, it's important we look at the accelerations and the directions of them. If we look at the diagram, acceleration in x of the coat will be equal to negative acceleration in y of the hanging mass. If we set up the net force in x of the coat, which will be equal to the tension 1 minus the static friction. This is equal to the mass of the coat times the acceleration. By solving for tension, we can say that mass times acceleration plus the friction is equal to tension. The tension between the coat and the string. Then we set up the net force in y of the hanging mass, which equals the tension 2 minus its mass times gravity, which is equal to mass 2 times acceleration, but negative acceleration because it's moving downward. Then we can solve for tension 2, which is equal to mass 2 times gravity, plus, for the the product of negative mass 2 times acceleration, so tension 2 equals mass 2 times gravity minus mass 2 times acceleration. Then we can equate tension 1 and tension 2. So take the two equations, when tension 1 and tension 2 set them equal to each other, like this. The next step is to solve for acceleration.
And by solving acceleration, it's just simple math. Using simple algebra, use this equation right here to get all the variables to get the variables that you want on one side, which is acceleration right here. And then you solve for a, pretty much very basic normal algebraic steps. You finally get the final equation, which is a equals m2 times g minus f of k all over m1 plus m2. We all have these variables, the solutions to these variables earlier on somewhere here, with fk equaling 11.76, m2g equaling 78.4, and then mass of 1 equaling 6, and then the mass of 2 equaling 8. And we finally solve for acceleration, which equals 4.76 meters per second squared.
The last step is to solve for the tension. And given the acceleration, we can plug acceleration into either of the two tension formulas we made earlier. you plug into either formula, including using the kinetic friction, you get 40.3 newtons.